is Dr. Esther Trufan, and in this video, I'm going to demonstrate a gas-forming reaction. For this experiment, we're going to need some equipment. For us, that means a scale, a graduated cylinder. I'm going to use a 50 milliliter one, but you can use a larger one if you have it. I will also use a 500 milliliter Erlenmeyer. I will need a ruler, some ribbon, and I have this colorful one. I will need a balloon to contain my gas, something to scoop my baking soda with, and then finally some scissors because I may need to do some cutting later. As far as my chemicals are concerned, I only need two. One of them is our baking soda, and the other one is a 5% vinegar solution that I already transferred into a beaker, but I will add more because for this experiment, I will need 150 milliliters. Now, I could just say I used my beaker to measure the 150 milliliters, but I would like to be a little bit more accurate than that, and I will be using my graduated cylinder today. So for the setup, the first thing I need to do is weigh my baking soda. I will turn on my scale, and when it says 0.00, I am ready to set up my measurement. To avoid any loss of material due to transfer, I will try to do my best to limit the number of transfers that I'm doing. So I will slide my balloon inside the Erlenmeyer and expand it on the inside, place it on top of my scale, and tear it. Now I'm going to measure into my balloon 2.4 grams of baking soda. And I'm going to use the sharper end of this spatula because I need the baking soda to be oriented towards the hole. This is a little bit more. It's 2.48 grams of baking soda. And with that, I am done with the baking soda. And I will remove the balloon from the top. The baking soda is all contained within, so I can just set it down and it will be fine. Next, I am going to measure my 150 milliliters of 5% vinegar solution inside the Erlenmeyer. For this one, though, I will start by placing my Erlenmeyer onto the scale and recording the mass of the Erlenmeyer by itself. It is 155.48 grams. Next, I'm going to add in 150 milliliters of 5% vinegar. If I have a 50 milliliter graduated cylinder, that means 3 measurements. If there are bubbles, we have to wait until they go away. So for our first measurement, we have 49.9 milliliters. This one is just a little bit less at 49.6 milliliters. And then a final measurement. I ran out. I could add more, but it is very close. It is 46.0 milliliters. So I will consider this close enough to 150 milliliters. I transfer this over. And I will record the mass of my Erlenmeyer with the approximately 150 milliliters of 5% vinegar solution. For me, that is 299.35 grams. I will set this aside for now. And I am done with my volume measurements. The next thing I'm going to do is utilize my Erlenmeyer that has the vinegar inside. I will take my balloon with the baking soda and carefully stretch it over its mouth from the outside. And if I did everything well, then my baking soda should still be on the bottom. Very gently and carefully, while holding the balloon in place, I'm going to begin transferring the baking soda. Clearly, there is gas formation and the balloon is growing. We need to swirl it a little bit to make sure that there is good contact between the baking soda and the vinegar solution. And then we let it mix until all the bubbles go away. It seems to be ready. So I pinch it, twist it a couple times, and when it's twisted enough, I remove the balloon from the top of the Erlenmeyer and then do my best to tie it into a knot. And now we have a balloon. Now it's not exactly a sphere, but if we compress it a little bit, it might resemble one. Now that we have all our carbon dioxide contained inside our balloon, it is time to find out everything that we possibly can about it. The most important thing is to find the volume. And because we can't really submerge this in water or find a graduated cylinder large enough for that, we're going to use an alternate approach. I will use a ribbon. I will place one end of the ribbon, and then I'm going to go around this balloon that is now turning into somewhat of a sphere. And where the two ends meet, I'm going to make a note to myself, and I will cut the ribbon. The length of this ribbon is the circumference of my balloon. So all I have to do now is figure out what the length is. And for that, I'm going to bring in a ruler. I will place the ruler on the bench top and then stretch my ribbon, place one end at the 0 centimeter mark, and then stretch it out until the end of the ruler. If it goes beyond the markings of the ruler, I'm going to make a small cut or an indentation at the 30 centimeter mark. And where that ends, I will place again to the 0 mark and measure it again. So the last bit that exceeded the 30 centimeter mark, 0.8 centimeters. So 31.08 centimeters is the circumference of my balloon. Knowing the circumference of a sphere allows us to calculate the radius of that sphere. And from radius, we can later find, through calculation, the volume of our sphere. And this gives us the volume of the gas that is inside the balloon. So that's one of the key pieces of information here. The other bit is the pressure. The pressure of the gas inside the balloon and the pressure of the atmosphere are exactly the same. So on the day when you are conducting your experiment, it is important that you check your weather forecast, because usually on the same app, you will also find the atmospheric pressure of the day, and make a note of that in your notebook. The other thing that you will need to record is room temperature. This could be typically 25 degrees Celsius, but don't take that as a fact, because every room on different days could have a different temperature. At any point, just place a thermometer on a bench top and record the temperature of the room at the time of your experiment. Because your experiment is running at room temperature, both your Erlenmeyer and your solution is likely to be at that temperature. So now we know volume, pressure, and temperature. And from these three properties, we can easily calculate the fourth one, which is the number of moles of gas involved. So what gas is inside here? Carbon dioxide. And because we're collecting the gas over water, we may also have water vapor. So that temperature that you collected earlier is really important, because now you're going to use that to determine the partial pressure of water vapor at the temperature of your experiment. So that's one, and you will be able to calculate the actual yield in moles of your carbon dioxide that was collected in the balloons. But that's not the only calculation that you can do here. The other one is associated with how much carbon dioxide was released, because we are not 100% certain that we captured all of it. There was a little bit of a hissing sound when I removed the balloon. And it is likely due to us losing some of our carbon dioxide. So we bring our scale back one more time. We turn it on and make sure it says 0.00. This now contains the Erlenmeyer, the 150 milliliters of vinegar, for which we know the exact mass, and we also know the exact mass of the baking soda that we intended to add. We're going to place everything on our scale and collect the mass of what is left over. And in this case, we have 300.96 grams. From this experiment, now we can calculate a second option for the number of moles of carbon dioxide. For that, we're going to use the original masses of the Erlenmeyer with the vinegar and the baking soda. And we're going to subtract from that sum the mass that we just collected. That difference is going to give us the amount of gas that was released as the result of the experiment. And that gives us a second way to calculate the number of moles of carbon dioxide released. If we have two number of moles of carbon dioxide, that means we have two experimentally determined moles, which both count as the actual yields. For the theoretical yield, we just need to determine which one is the limiting reactant, our 2.48 grams of baking soda or our 150 milliliters of 5% vinegar solution. Once we make that determination, we can calculate the number of moles of carbon dioxide that was released. And from actual divided by theoretical yield, both expressed in moles of carbon dioxide, we can calculate the percent yield of the carbon dioxide that was created and the carbon dioxide that was contained within the balloon.